We have started from scratch again, and the only thing we took from the concept one is the idea to use the potential of an electric powertrain, not just to build supercars, but to create the next generation of hypercars. The most exciting challenge was to achieve our extreme performance targets whilst conceiving a timeless and functional design.
We are working in C2 Aerodynamics for 2 years. We started to develop it from early stage of design sketches, studying and optimizing the vehicle body in different 2D sections and then moving to 3D analysis.
The idea behind the C2 was to further develop the design DNA, what we have established with Concept 1, to develop it further, to bring it to the next level, and also form the proportions in order to show the electric propulsion system. The car has a very unique drivetrain, so we wanted also the shape and the proportions to reflect this. The car is alive with technology. Some of its parts even move, and that not only improves its performance, but also adapts to certain driving scenarios. One of the active aerodynamic parts in this car is the big rear wing. The wing in this position actually helps reduce the drag, and when it goes up, it increases downforce. But when the wing is up, also more of this radiator outlet becomes more exposed, and the suction underneath the wing even helps with the mass flow. So not only it adapts to the global balance of the car, but also to the performance of cooling. The wing performs together with the diffuser flap, but not only that, because if you would only move the rear, the balance, the aero balance would be changed. So this wing also performs together with the flap on the hood and on the bottom of the car. This actually changes the mass flow also on the front, but also balances out the overall forces on the car. Most cars are an abstraction of a wing profile, so it naturally tends to generate lift. And with a really low and extended splitter, a flat floor and a big diffuser, we try to counterattack that. To improve consumption and therewith the range of a fully charged battery, we reduced the drag as much as we could, but without making the design look blunt. But we wanted to keep a more distinct and strong character that a Rimac car should have. For all the bits, we had to closely collaborate with all departments, but especially with our experts from aerodynamics to improve performance and also fulfill targets that we set ourselves. One of the main goals was to either redirect the air where we want it to be or to restrict the air from going where we don't want it to go.
For aerodynamics development, we are using CFD simulations, which stands for Computational Fluid Dynamics. CFD is numerical analysis that help us to understand better the flow field around the vehicle body. What we are actually doing in CFD, we are solving a complex set of Navier-Stokes equations in the composed domain. Volume of the air around the vehicle body is split in more than 70 million elements, and then for each element we are iteratively solving those equations. At that point we have to use supercomputer power. Bura has almost 7,000 cores, and a number of those cores are helping us to resolve the system of more than 70 million elements, what brings us to the final solution. In CFD, we do hundreds, sometimes thousands of iterations, implementing different strategies and geometries. Every time we change something, we need to check this with homologation, engineering and design if those changes are feasible and acceptable. Finding the right compromise can be sometimes really tough, especially with Adriano. Low drag coefficient of electric cars is very important in order to extend the range and increase the overall efficiency. The lowest drag coefficient that we have measured on C2 was 0.28. During high speeds, active aerodynamics is crucial because it balances the high downforce in the corners with high efficiency in a straight line. After we have a status that we are happy with, but still before we invest in tooling, we validate and correlate our results in a wind tunnel. For CFD correlation, we are using full-scale model, which is purpose-built for the wind tunnel test. It was built in a way that we can exchange and test the relevant parts quickly. The model consists of important elements for aerodynamics: fully functional active aero components, realistic suspension and brakes, fans, the realistic pressure drop through the radiator cores, as well as the rotating wheels. It's important to mention that we have done the testing before releasing the tooling into production, so any change could be still implemented in the production car. We split the wind tunnel testing in different sessions, where each session was focused on one area. We focused on drag coefficient, lift coefficient, and at the end we were focusing a lot on cooling efficiency. During each session, we repeated several tests. We did force and pressure measurements, as well as several sensitivity tests, for example, ground clearance, lateral sensitivity, and acoustic sensitivity. On all of that, we included the active aerodynamics, which added even more complexity to the test. With this model, we got as close as we could to the real car. CFD results were very close to the experimental. For example, we had only 2.4% of average deviation between the simulation results and the wind tunnel testing. This proves that our approach, numerical simulations and solve scripts are very accurate. In the end, it is very important that we merge CFD simulations, the wind tunnel testing and the track measurements. Track testing gives us an additional value of a driver feeling that confirms all our engineering effort for C2 project.
We did hundreds of loops and iterations where we simulated, tested and optimized each part. So every surface, every line, every opening has a specific function and purpose. Finally, we fulfilled our targets whilst keeping the original design idea, which was anyway driven by performance.